The next topic in our physics section of this course is a wave. A wave is fundamental in application of physics and especially plays a role in different science and technologies, application of science and technologies. If we see in our daily life, everyday life, waves are everywhere and are critical in most of the technology we use. For example, communication technologies like radio, television, and mobile phones, all these technologies rely on electromagnetic wave to transfer information over long distance. Uh, Also, when we check weather, we are basically using radar and satellite systems that use microwaves and radio waves to track storms, atmospheric patterns, etc. Similarly, waves are also used in material characterization, for example, X-rays, ultrasound, etc. to both by physicists as well as material scientists. Waves are also used in energy transfer and technologies such as solar panels, wireless power transmission, etc. One very important application of wave is in medicine. Waves allow us to see inside the human body without surgery. Application of X-rays, sonograms, PET scans, MRI images. All this technology use different type of light and sound waves to give us a look inside a human body. So what exactly is wave? How do we define wave? A wave is a traveling disturbance that transfer energy from one point to another point, and this disturbance can be periodic, meaning repeating, or it can be a brief disturbance called a pulse disturbance. And broadly speaking, the wave can be categorized into two types. First, mechanical wave. These waves transfer energy by vibration of a medium. Uh, and when we say medium, we are basically talking about matter like air, water, metal, etc. A great example of mechanical wave is an ocean wave, or the sound from a guitar string. The mechanical wave moves because the mechanical wave transfers energy from one point to another point because of molecular vibration. One molecule bumps to other molecules, and this bumping from one molecule to another molecule will transfer energy from one point to other point. And the second type of wave is electromagnetic wave. Uh, and for electromagnetic wave, unlike mechanical wave, these waves don't need a medium, meaning electromagnetic wave can also can move in vacuum where there is no medium. We don't need a medium for electromagnetic wave, and this electromagnetic wave transfer energy through a disturbance in an electromagnetic field. So when there is a disturbance in an electromagnetic field, it will generate electromagnetic waves, and an excellent example of electromagnetic wave is light. For example, the light from the sun travels to earth in the form of electromagnetic waves, and it includes uh, visible lights, ultraviolet, infrared radiation, etc. And the light can travel from such a far distance in vacuum because they do not need any medium, so they can also travel through the space. And we can also categorize a wave based on the direction of the movement, uh, direction of the wave. And the first category is uh, transverse wave. Transverse wave is a wave in which the oscillation uh, or the disturbance, we can also call it disturbance, is perpendicular to the direction the wave is traveling. uh, for example, here we can see when we move this spring up and down, we can see there's a motion from here by hand. It's when we move this spring up and down, we can see the wave is traveling from left to right, meaning it's the energy transfer is from left to right perpendicular to the movement. So the motion we gave to the spring was up and down, and the direction the wave is traveling is perpendicular to the disturbance we created. So the wave oscillates perpendicular to their direction of propagation. So the wave the direction of a wave is perpendicular to the oscillation. We can also see from this image here, the spring is moved up and down, and then it will start moving like this, transferring energy from this point to this point. And we should also note that even though wave looks like it's moving, rather the material itself is not moving, because the spring on your hand is still there, but it's transferring the energy from one form to another form without moving the material from one point to another point. So basically it's transferring the energy. And generally the transfer wave is represented like this. If it's periodic, this is how we will generally see a transverse wave, where this y-axis is amplitude. We will talk about this terminology in the next slide. And your x-axis is time, meaning as the time passes, the motion moves at certain point with a certain height from starting point, and as the time passes, it moves from one point to other point at certain height. And we can see here in the video, it starts from here and moves like this. And the second kind of wave is longitudinal wave. Longitudinal wave is one where the oscillation is parallel to the direction of motion. So if you look at here, the oscillation is in this direction, is moving to and fro, and the motion, the wave is also, we can see here, wave is also moving in the parallel direction to the oscillation provided oscillation. So basically the energy transfer and the oscillation are perpendicular to parallel to each other. And one great example of longitudinal wave is a sound wave. Sound travels, sound generally, the sound in ear travels in longitudinal wave, and this longitudinal wave is generally represented as in case of sound wave. So this is how the sound wave travels, and then you will have a dense point here again, and then few here, and then again there will be dense. Similar to what we see in the spring, we can see here, and it's moving here, it's moving here. So basically what happens is it condensed at some point and then expands at some point, and this expanded part is called rarefaction, and this is sometimes called condensation and sometimes called compression. So basically similar to what we see in the spring example, here also move in similar way. It form a very dense, all the particles are sorry, this burst of energy is very high here because of energy because of the particles present in this section, and then this is similar to what is open here, and then again there's a compression, again there's a rarefaction and compression, and so on. So energy is transferred from this point to this point. And more terminology, basics of waves. uh, Regardless of their type, both for a longitudinal wave and a transverse wave, we can see here in image. The first image is how longitudinal wave is represented generally, the similar way as here, where we have these condensations and rarefaction. We can see here we have a condensed part here, and then rarefaction, and then again condensed part, rarefaction, we call it compression, and then compression, expansion. This is called expansion as well as rarefaction, and sometimes this compression is also called condensation. And the first terminology is wavelength. Wavelength is generally represented by Greek letter lambda, and it is lambda, pronounced as lambda. This is the distance between two identical points on a wave. Like if we look at this transverse wave in the second image, the amplitude is distance, the wavelength is distance from one peak to other peak, or from one trough to other trough. So basically distance between similar points. For example, we can also take this point, and this point, this will also be a wavelength. And the second example, and in term of longitudinal wave, we will again select a similar point in two part. So if we start from this middle of this compression, then we will move to a similar point in another compression, and we will calculate the distance from this point to this point, and that is the wavelength of the wave. And second is amplitude. This is the maximum displacement of the wave from its resting or equilibrium position, and here in the longitudinal wave, since this is the midpoint, the amplitude is distance from this point, the average point to either end of the wave. And for a transverse wave, again we have a midpoint, the average point, and from average point to one of the peak, the distance from average point to the peak is amplitude. Since it's periodic, either we can take height in positive direction, negative direction, it should be the same height, and we call it amplitude. And then we have frequency. This is the measure of complete cycle that passes a specific point in 1 unit of time, meaning before that we need to sorry before that in order to understand frequency, we need to understand a cycle. So a cycle is when we start from this point, so we will pass through this point, and when we reach the similar point here, this is a complete cycle. So this is basically a one cycle. And if we look at here, and this is the second cycle, third cycle, etc. So when we call frequency is basically, so we say this x-axis here is in term of time. So if we take a 1 second unit time, 1 second, and count how many cycles are there within this 1 second time interval, that will give us the frequency. For example, in this case, let's see, if from here this is 1 cycle, so if this is 1 second, it takes 1 second to complete this 1 cycle, that means the frequency is 1. And the unit of frequency is, since it's saying unit time, so frequency is per second, also read as per second, or we can also, we generally also use hertz, and it's written as Hz. So the unit of frequency is hertz or per second, and it's given by frequency is equals to 1 over time period. And before that, we also need to define time period, and since we already know what is a cycle, the period of a wave is basically the time taken to complete this one cycle. Whatever time is taken for the wave to complete one cycle is called period, and the frequency and the period is related by this equation. Frequency is equals to 1 over period. And the wavelength and time period, if we know the wavelength and period of a wave, we can also calculate the speed of wave, and as we know, speed is, when we say speed, we are basically talking about change in distance, or we can just say distance over time taken, right? And what did we say when we defined the wavelength? We said wavelength is the distance The distance from this point to this point is called wavelength, and we also say the time period to complete a cycle. Basically, the wavelength and cycle are related, right? The length from this point to this point, when the wave completes a cycle, is basically the uh, wavelength. That means the distance covered by the wave in one period is given by the speed of sound. So in at in one period it will cover the wave will cover 1 lambda distance. In t is period, t time, the wave will travel lambda distance. So if we want to simplify in the word, basically what we are saying is in t time, in a period, the wave will travel lambda distance, and if we know the distance and time, basically we can calculate the speed of the speed of the wave. And we talked about it in the previous slide. The frequency is reciprocal of the period, and the unit is per second or hertz, and the relation is frequency is equals to 1 over time period. And if we mix this equation, b equals to lambda over t and f equals to 1 over t, we get velocity or speed of sound is equals to lambda times frequency. We can also write it as speed is equals to lambda is wavelength times frequency. Now let's look at an example. A sound wave with frequency of 60 Hz, so frequency is 260 Hz, has a wavelength of 1.27 meter. Wavelength is given, wavelength is 1.27 meter, and is asking what is the speed of this sound wave. And just before in the previous slide we derived that speed is equals to frequency times wavelength, and the frequency here is 260 Hz times distance is wavelength is 1.27 meter, and we also know 1 Hz is 1 per second. So if we simplify this, 260 over second 260 per second times 1.27 meter is equals to this I already calculated here. This is 330, and this is meter, and this is per second, so 330 meter per second. So the speed of the wave with the frequency of 260 Hz and wavelength of 1.2 meter is 330 meter per second. And this is the close approximation of the speed of sound in year. Speed of sound wave. And the speed of sound wave requires As we said, sound is a mechanical wave, so the sound requires a medium to transfer from one point to other point, and this speed of sound is very much dependent on temperature, intermolecular interaction, or intermolecular strength of the air particles, and inertia of molecules. For example, if there are heavy uh, molecules on the air, the speed of sound will be different compared to if the air is made up of light air. And for if we are looking at the same air and measuring the speed of sound in the environment, the main factor that affects the speed of sound is temperature, and there is very weak uh, dependence on pressure. So the speed of sound in air is very much dependent on the temperature of the air, uh, and the speed of sound has a very weak dependence on the pressure. And when we say it depends on temperature, it is the if the temperature of the air is increased, the speed of the sound will also increase. So they are positively correlated, and the speed of sound wave in air at 0 degrees Celsius is 331 meter per second, and the speed on a solid structure like steel is 5940 meter per second. And we can see here the speed of the sound is higher in solid structure compared to uh, air. And we can also interpolate this information, and we can say the speed of the sound is lowest for air, and will increase a little bit for liquid, and will be highest for solid structure. Now let's talk about loudness. Since we are talking about sound wave, it makes sense that we are talking about loudness. Loudness is how we perceive sound, and it's directly related to physical property of wave called amplitude. And so loudness is the perception of is our perception of sound, and it directly it is directly dependent on amplitude. And this loudness is measured in terms of the intensity, and the intensity itself is defined as the measure of energy the sound wave is carrying per unit area per unit time. So basically, uh, the intensity. So we know the wave is basically energy transfer, right? And we need to define power first. Power is energy or work over time. So this is how energy power is defined: work per unit time, or rate of work. And we can see here intensity is sound wave carrying energy of the sound wave is carrying per unit area per unit time. So work per unit time per unit area, and we know work is basically change in energy, right? And work over time is power over area. Or in other word, we can also say if this is a area we are interested in, and for example these are sound wave. So basically what it's saying is how much this sound wave passes through this area in a unit time. So that will give us the intensity. If this is area and we're looking at 1 unit time, so how much this energy is transferred from this the reference area in 1 unit time is called the intensity of is called the intensity, and this intensity is used to measure the loudness and the loudness itself is dependent on amplitude, because the energy transfer or the work done is directly dependent on the amplitude. And the unit of loudness is measured in decibel, also written as dB in short. And if we want to look at the equation, this sorry equation of how this decibel is calculated, it's calculated as a logarithmic value and given by sound intensity sound intensity level is equals to 10 log 10 intensity over reference intensity. So basically this decibel point is calculated with reference to some non intensity, and generally that intensity is the intensity of the sound, the minimum sound wave decibel, and that's audible to human ear. And here we should also know that since this is a logarithmic scale, we do not need to go for look more on this equation. We will not do any numerical problem since we are not well versed on using the logarithmic yet, but we will also we will just look at how this logarithmic scale will work. To put this in perspective, a whisper the decibel scale, since it's a logarithmic, this means that even a small change in decibel will represent a very large change in sound intensity. For instance, an increase of just 10 decibel, if the intensity of the sound changes by 10 decibel, it could be uh, perceived as loud as twice the sorry it could be perceived twice as loud as it was before, even for just 10 decibel increment. And that is how the log scale works. And let's look at some example of the noise level. We talk about how the decibel scale is logarithmic and small change in decibel represents a very large change in sound intensity. Here the example is also here. So 10 decibel, an increase in 10 decibel corresponds to a sound that is perceived as roughly twice as loud. And some of the example of decibel value are here, are least needed for hearing. So this is the lowest a human ear can hear, and the response as we perceive is barely perceived, so we can barely hear it, and that is generally 0 decibel. And whisper is very quiet, about 20 decibel, and the talking with easy to hear noise level is around 65 decibel, and the jet plane we see, which we perceive as a very loud, is generally 120 decibel noise level. And understanding these waves and sounds help us appreciate how how applicable these waves are in our day-to-day life, from uh, medical field to aerospace, and even exploring the outer space.